in Department of Mathematics in School of Applied Sciences. He is a coordinator of Center of Computational Mathematics, Centurion University of Technology and Management. And Sir has been performing his duties as the professor of mathematics. Along with that, he has also worked as a campus coordinator for the Center of Computational Mathematics at Centurion University of Technology and Management. He has already discharged his responsibilities as the registrar of the university from the year 2011 to 2017 and Dean School of Applied Sciences from the year 2017 to 2020. He has over 25 years of teaching and 12 years of research experience. He has published 70 plus research articles in peer-reviewed and indexed journals. He has 15 plus book chapters in reputed book series and 4 patents to date to his credit. He has authored 8 books and has produced 10 PhD scholars. Sir has delivered invited talks and chaired sessions in 30 plus national and international conferences. He has also conducted many events like AICT, Atal FDP, international conferences, webinars, and symposiums, etc. He is the reviewer of 20 plus international peer-reviewed journals. He has developed one domain course on CFD, skill course on quantum computing, and 12 courses of MSc, BSc, and BTech programs of the university. He has visited Mauritius, Botswana, and Nepal to deliver invited talks. He is a life member of IST, OMS, ISRD, and IAENG, IMS, and LSDB. So, once again, on behalf of our Phaltan Education Society's College of Engineering, Phaltan, I heartily welcome Dr. Ashok Mishra, sir, and request sir to start his session. Please, sir.
Thank you, Professor Amit. Is my screen visible?
Yes, sir. Screen is visible.
Okay. So, good morning, all the dignitaries of Phaltan Education Society's College of Engineering, and I am thankful to all the members, including Chief Patron, and all the members of the college for conducting such an international conference on advancements in science and technology on 27th and 28th March 2024. And thankful to them also for giving me an opportunity to be the keynote speaker of one of the sessions. Thank you. So now, my screen is visible. Is it okay? Hello.
Hello, sir.
Is my screen visible? Hello?
Yes, sir. Screen is visible.
Okay. So, today's topic is the latest developments in the computational fluid dynamics modeling of nanofluid flow. Because there is a topic on nanoparticles and nanofluid. That's why what has been done already and what we have done, what is the novelty of our research. So today we'll discuss all those things in a nutshell. Though there are some mathematical terms, but in a nutshell I will explain what is actually going on, why, what is the advantage, disadvantage of nanofluids, and why it is required. Why nowadays nanofluid application is required for that one. So the outline is like this: introduction, applications of nanofluids, advantages of nanofluids, disadvantages of nanofluids, dynamics of nanoparticle motion in a base fluid, which leads to the modeling. Then mathematical models for nanofluid flow and heat transfer. How many earlier from the past, how many modelings were there and how it is being improved. Also, especially by our team. Then CFD techniques for nanofluid flow simulation. Then final conclusion. If time permits, I will give a case study if time permits. So generally, what is nanofluid? Then if we say, why it is required? Because generally nanofluid is considered or applied for a cooling system or heating system. Okay. So generally earlier what happened? Industry people or R&D people, they had been using the direct base fluid. The base fluid may be water, toluene, ethylene glycosol or oil. But in due course of time, it was revealed that the gel base fluid, the thermal content of base fluid is much less total, and it does not work properly if we apply to any heating system or cooling system. Then slowly scientists and industrialists, they thought that if we diffuse nanoparticles, earlier what happens? Micrometer particles were there, millimeter particles will be there, were there. So first they diffuse micro and millimeter nanoparticles, micrometer particles into base fluid. Then they thought, what happens? There were some sedimentations, okay, they settled down. So due to which, again, thermal conductivity, there's an imbalance in the thermal conductivity occurred. Then they thought, if we reduce the diameter of the particles, any small nanoparticles, if we consider what is happening, because it is not settled down. Through fluid, if we apply some bigger particles, micro or millimeter particles, they will settle down. That one. Suppose we can say soap water soap. What happens after some time? The soap particles will settle down. It will not move in that way. Unless you stir it again, it will not flow in that way. So that's why it was decided, why not we go with some nanoparticles? So that nanoparticles with the flow of fluid, it will pass and it will have, immediately it will not settle down, and which could enhance the thermal conductivity of fluids, base fluids. That's why nanofluid is a colloidal suspension of nanoparticles in a base fluid. When you diffuse the nanoparticles, 10 to the minus 9, okay, your nanometers, 10 to the minus 9 nanometers, this type of if you consider the size of nanoparticles, if you diffuse that one, then what is happening? So nanofluid is a colloidal suspension of nanoparticles in a base fluid. Nanofluids are characterized by base fluid, water, toluene, ethylene glycosol or oil. The nanoparticles are either metals or oxides or carbides or carbon nitrides or any other mixture. Now earlier it was only one nanoparticle. Now it is hybrid nanoparticles. With the base fluid, 2 types of nanoparticles are diffused. Then trilane nanoparticles, 3 nanoparticles, 3 types of nanoparticles are diffused. So any combination also we can diffuse for that one. So why mathematical model? Am I audible? Hello? Hello?
Yes, sir. Yes, sir. You are audible.
Okay, because there is a network problem, that's why I'm telling. Okay, fine. So why this mathematical modeling is required? Because nowadays CFD modeling, why it is required? Earlier what happens? When we go to your experiment setup, It takes so much of time. We have to invest money, and if that fails, again we have to invest. So time waste, money also waste, and resource person also will be more. So three ways we are losing. But if we go with CFD modelings, what happens? It is not required. First we go with simulations, and immediately in a laboratory scale not required. First we go with simulations, and a computer modeling is required. If we get some data, basic data, based on that we can go with the experimental cases. Instead of blindly go with the experimental cases, now it is required first to go with the mathematical modeling, get some data, based on that go with the your mathematical your laboratory scale models for that one. So exploiting nanofluids in thermal systems, why mathematical modeling is required? The enhancement of thermal conductivity of nanofluids, no best technique for the modeling of nanofluids till date. There is no particular technique, modeling technique is there, which we can say that this is the best model for the thermal conductivity of nanofluids. It is not that till date. Still, your models are going on how to enhance the thermal conductivity of nanofluids for that one. Then already I told you high cost for the production of nanofluids. If I go with the laboratory scale, we have to invest money, and this is a high cost. And if that fails, then again you have to invest. So to avoid that one, mathematical modeling is highly essential for that one. The numerical assessment of thermal performance of a system. Then after modeling, we can go with the numerical assessment. Then based on that, what is the thermal performance? Then we can go to laboratory scale. What is the application of nanofluids? Nowadays, you can see any industry, these are the applications. There is no place in industry or R&D section where nanofluid is not required. So boiler exhaust, flue gas recovery, solar water heating, refrigeration, these are limited. There are many applications are there. Refrigeration, defense and space applications, thermal storage, nuclear cooling system, electronic applications, biomedical applications, transportation, petroleum industry, and environmental remediations. So these are not limited to. Wherever you see nowadays, highly essential nanofluids. Because when we deal with any machines or any system, external system, cooling and heating is a very crucial point. So, what are the advantages of nanofluids? So, advantage is that the thermal conductivity of nanofluid is higher than the base fluids. I have already told you, if you consider only base fluids, the thermal conductivity, and after adding the nanoparticles or diffusing the nanoparticles into base fluid, automatically thermal conductivity is higher and having great potential and more efficient for a cooling system. Then high specific surface area and hence more heat transfer surface between particles and fluids. So if you diffuse the nanoparticles into base fluid, the surface area will be high. Then automatically it will sustain. Heat transfer will sustain between particle and fluids. The nanoparticles stay suspended longer time compared to microparticles. Already I discussed that one. Because microparticles, they settle down. But nanoparticles hardly settle down. They are suspended in the longer time for that one. High stability and high thermal conductivity. Reduced pumping power. Nanofluids are more suitable for rapid heating and also cooling systems. Immediately we can heat the setup. Also it can use for the cooling system. Both the things are there. And nanofluids, as compared to your millimeter and micro-sized particles, if you diffuse into fluid, base fluid, nanofluids, if you diffuse, it has less erosion, clogging, and abrasion as compared to other conventional fluids. And if into conventional fluids, if you diffuse millimeter and micrometer particles for that one. Then what are the disadvantages of nanofluids? That's why we are working on the disadvantages of nanofluids. How to achieve the advantage over disadvantages for that one. Higher viscosity, lower specific heat, and it is high cost of nanofluids and difficulties in production process. Poor long-term stability of suspension. It is not suspended. But long-term basis, if you see, it is not suspended. It is settled down. Then we can go with dynamics of nanoparticle motion in a base fluid. What is that actually? Whatever things, a millimeter or micrometer or nanometer size particles, when they are diffused into fluids, what happens? Some forces are exerted on the fluid particle, your nanoparticles. So if we diffuse your micrometer size particles or millimeter size particles, there are many forces exerted due to fluid motion exerted on the particles. But when you go with the nanoparticles, all those forces are not required. Suppose a two-phase flow, all forces are required. Many forces are there. Because due to the particle size, all the modeling or all the forces are not required. Some are discarded, some are required. Because of that forces, we can model the nanofluid with the nanoparticles. So, first thing is, the knowledge of dynamics of particles, nanoparticles in base liquid is a prerequisite for accurately describing the process of heat transfer, nanofluid flow. There are a wide range of forces that act on particles suspended in a fluid, but only a fraction of these forces are significant for the nanofluids due to the small particle size. Okay. Then in general, forces acting on particles suspended in a fluid include, these are the forces, the base fluid, surrounding walls and solid surfaces, other nanoparticles, external magnetic or electric fields. If you go for MSD flow, then external magnetic field is required also, and an acoustic field. Then, which are the forces? If nanoparticles are diffused through the base fluid, which are the forces and what are the modelings that we will discuss? So, forces acting on nanoparticles by base fluid. So, first is drag force. Drag force means what? We can say, we know also aerodynamic drag. When particles move through a base fluid, nanoparticles when move through a base fluid, an opposite force is applied to the, or a reverse force is applied on the nanofluids, the nanoparticles, due to the motion of the fluid. That is called drag force. So, if you model the phenomena, this is the mathematical formation, drag force based on Stokes' law. It is called Stokes drag force, which is modified by a friction factor F and is given by Stokes. So, Fd equal to minus 3 pi dp mu p Vs F. And these are the cases. And the last one is here, CD. CD means coefficient of drag. It is Fd by half rho V square A. Rho means density, V is the velocity, slip velocity. That means when particle and fluid both will move, there is slip velocity because they will not move in a same way. If a fluid is more, particle is less. They will not, in unison with fluid, particles cannot move. So there is a slip velocity. There is a difference between the two velocities that we call slip velocity. So Vs equal to Vp minus Vf, whatever things meant. Then lift force. When we can say that when the aeroplane takes off, there is a lift force. The drag force, in opposite side, lift force acting. So there are two types of lift force. This force acting on a nanoparticle moving in a liquid is composed of two independent forces. There are two types of lift forces, Safran and Magnus forces. And both when we combine the total lift force we can get. Then what is Safran force? The shear force induced on a particle moving with the fluid. Shear means tangential force, we can say like this. Shear force. Okay. So, due to this is the FLS is equal, this is the expression, which is the Safran force. This is one type of lift force. Then Magnus force. When particles move through a fluid, they collide with each other, collide with the particles of fluid, they collide with each other, or suppose it flows through a channel or something, they also hit or to the walls, they start rotating. The particles start rotating. So when the particles start rotating, what happens? Automatically, it's a angular velocity automatically appears. takes place. And it is given by omega k. So it is like this. Okay. So flow in the x direction, the rotational velocity omega k in the z direction, magnetic force will be force in the y direction. Like this we can consider the things. Okay. So this is the Safran force. This is the Safran force. And both the Safran and your Magnus, if we put together, we are getting this. This is the case. You are getting F equal to 1. Both the forces, when you put, you are getting lift force. Then unsteady flow forces. Unsteady means it is with respect to time, it varies. So unsteady flow forces on particles can be divided into 3 groups. One is inertial pressure gradient force. Then second one is virtual mass force or other mass force. Then Bassett history force. 3 cases are there in different cases. Then your inertial pressure gradient force. What is that? 3 types of cases are there. So consider a spherical particle with diameter dp and volume this one. When immersed in a fluid with density, the force acting on a particle due to pressure gradient is given by the integration over all the volume. So these are the expressions for the inertial pressure gradient forces. And finally, the form of inertial pressure gradient force is given by Fd equal to this one, inertial force gradients. The next one is virtual mass force or added virtual mass force. What is that actually? Then the force acting on an accelerating particle in a liquid. Because when you are diffusing the particles into waste fluid, it is already in accelerated form. So the force acting on accelerated particles in a liquid is higher than the force acting on the same particle in vacuum. Obviously, because of the need to also accelerate the surrounding fluid elements which are set in motion by the particles. Then what happens at one? When you add the mass force, it is, you can say it is an additional force. It is an additional force that is needed to act on a particle inside a fluid to change its velocity in comparison with the case in which the particle moves in vacuum, obviously. So you can say puff A equal to this one, added virtual mass force. You are getting that one. Then Bassett history force. So Bosiniak approximation depends upon heat transfer actually. Unsteady drag force is there. So Bosiniak approximation is there. We can call it Bosiniak Bassett force, history force, or simply Bassett force. Or we can call it also unsteady drag force. So it is an unsteady force due to velocity change of a suspended particle in the viscous fluid. And the Bassett force we can consider eta BH equal to this one. This is the expression for a Bassett history force. Then the main and the heart of the thing is Brownian force. So when the particles are diffused into the waste fluid, what happens? They collide with each other, collide with the fluid particles, they move in a zigzag motion, which is called Brownian forces because of that. And it has a significant effect on the thermal conductivity enhancement or heat and mass transfer, both. It has the great impact on the heat and mass transfer enhancement of the nanofluids for that one. And first we can say Brown, 1827, was probably the first one. He has considered by observed microscope of the collision between grains of pollen of a plant with water molecules, which leads to random motion of grains in water. Then, in due course of time, based on Brownian concept, different authors, scientists, they start reviewing the things. They got different types of formulae for that one. So finally, this is the formula of Brownian force, whatever things may be. Now, this is another formula when provided after passing a specified time t, the t equal to this one. Then, in case of nanoparticles, the time may be just a hundredth of the second, particles diffuse from a region having high concentration of particles towards a region with a lower concentration via Brownian diffusion. In this regard, if the concentration phi, concentration means nanoparticle concentration. How much nanoparticles, amount of nanoparticles are added to the base fluid, that is phi. So, if that is the concentration, these we are getting the equation and modeling for the Brownian diffusion. Dou phi by dou t equal to dP grad square phi, where dP is called the Brownian diffusion coefficient. So, this is the mathematical modeling for the Brownian diffusion, where the dB expression is this one, for that one. Then, thermophoretic forces. What is thermophoretic forces actually? You see one thing, when the temperature gradient is inversely proportional to concentration gradient. I'm simply telling that one. Suppose there is a chimney you can say, put a chimney and burn it. Then put a plate or some pepper, something above that. What happens? Chimney, near where it goes up actually, okay, heat is more at the base level. But when slowly you are going up, automatically your heat is reduced. But what is happening? You see, if you put a plate, you are getting some particles. That means it becomes black. Black means what? The nanoparticle, the size of particles, they are totally stick to the plate. The concentration is more, but heat is less. That is called thermophoretic force for that one. And it is given by Ft equal to this one. This is the our expression for the thermophoretic forces. Am I audible? Hello? Hello? Hello?
Yes, sir.
Yeah, because in this I'm asking. Okay, fine. Okay, fine. So there are different types of expressions. FT, these are the expressions. Okay, so first expression given by Epstein, then second one broke. Then slowly it is developed and it was refined and different types of forces are coming. Now this is the latest one, FTVT, thermophoretic forces, this one. Then again he and Ahmad, they've also improved another, because I told you till date there is no such particular phenomena or modeling where you can say that this is the best modeling. So still modeling is going on. So different scientists or investigators, they investigate in different way. They are obtaining the for different conditions they are obtaining the formulae for that one. Then again, Michaelides also obtained this formula. Then next goes to interparticle forces. So what is interparticle forces? Interparticle forces become important, especially when the number of particles in a specific volume of mixture increases. However, what is happening actually? If the concentration of particle in the system is small, then what happens? If we say interparticle forces acting between non-adhesive particles may be safely neglected. And if we in these suspensions of adhesive particles, interparticle forces are therefore necessary at all values of bulk particle concentration. So interparticle forces, if aggregation not there, we can neglect. Okay. Otherwise, we have to consume that one. Then dilute and dense nanofluids. So what is dilute and dense nanofluids? Based on the solid volume fraction of nanoparticles, when particles are dispersed in the base fluid, Nanofluids, that means solid liquid mixture, can be classified in two general groups, including one is diluted, one is dense. So solid volume fraction is defined. How can we define it? It is a ratio of solid nanoparticles volumes to the total volume of mixture. So concentration, nanoparticle concentration will be nanoparticle volume by total volume into 100. That is the volume concentration. Okay. Then van der Waals forces. It is there also in physics. What are these forces? The van der Waals forces appears between molecules or tiny particles. Generally, how does it act? It acts generally on as an attractive forces. It has two types of forces actually. It is considered two type forces, or it is composed out of two type forces. One is London force, that is dispersion interaction. Second one is Debye force, dipole-dipole interaction. So there are two types of van der Waals forces. So the van der Waals forces between two rigid spheres form of the same material is given by this expression. This is the expression for that one. And van der Waals forces between a sphere and a plane can be estimated as this one. When equal to this is the expression for that one. Then electrostatic double layer force. What is that actually? Because the presence of ions in the waste fluid can result in the formation of an electrical double layer around charged particles automatically. When particles are diffused to the waste fluid, the particles, because of collision, they are automatically charged. Then there is a formation of double layer around the charged particles. And this electrostatic double layer, it will induce a force of very small range. Okay, and Hogg, Helly, Feuerstein, he considered the formula EDL, E of EDL equal to this much for that one. It is electrostatic double layer force. Then other interparticle forces are, we can consider like this for that one. Steric, electrosteric, depletion, capillary, salvation, structural, hydration forces for that one. And what are the external forces? The sources such as gravity, magnetic electric field, and acoustic oscillations that would create the forces which affect the flow and heat transfer of fluid. Nanofluid fields. And what are those cases actually? Some of them are reduced gravity force, Lorentz force, acoustic radiation forces. These are the three external forces applied to the nanofluids. Then next one is reduced gravity force. What is that actually? If it is the, when particles are diffused into a fluid, automatically we know that gravitational force is there, also buoyancy force is there. So due to this gravitational buoyancy forces, the reduced gravity force, which is the outcome of your gravitational force and buoyancy force. And it is defined by or expressed as this expression, Fg equal to this one. And this reduced gravity force, that can be easily neglected, usually in nanofluid flows due to ultra-fine size of nanoparticles. It does not have much effect on that one. So sometimes we can, if this, suppose let us say it is a dilute mixture. So for that one, this force is not required. Dense means it is required for that one. Then, like Brownian, this Lorentz force plays a vital role while modeling the nanofluid cases. And what is that actually? Generally, we know what is a Lorentz force. Suppose a fluid with an electrical conductivity flows in a duct under an external electric field E and magnetic force, field of force B. Then a force is applied to elements of fluid, which is called a Lorentz force. And what is the effect? How does it affect? It affects the velocity, magnitude, and temperature field in the thermal equipment. And Lorentz force, this is the called J cross B, and sigma of E plus B plus B plus D for that one. The one is conduction, one is convection. Two types cases are there. So this is the expression for the Lorentz force. Then acoustic radiation force. When the energy of sound waves can also be used to enhance the performance of thermal systems. Acoustic waves and sound waves, you can say. So the force means time average force acting on particles by acoustic waves is called acoustic radiation forces. So there are many studies, many investigations that have studied to determine the radiation force on particles in fluids. And since the acoustic radiation force is proportional to particle volume, okay, so it would be expected to be small compared to forces such as drag force. So if you compare this acoustic radiation force with the drag force, it may be neglected. Very small particle size, it is not required for that. Then next one is an overview of thermophysical properties. So when particles are diffused through fluid, base fluid, what are the thermophysical properties? So due to lack of experimental records on fluid properties, researchers have a strong need to calculate the values of effective thermal conductivity, density, viscosity, and specific heat. These are generally the properties of nanofluids. And what are properties of the thermophysical properties? One is density, specific heat, thermal expansion coefficient, electrical conductivity, dynamic viscosity, thermal conductivity. So when you model the phenomena, these parameters have to be considered. For different combination of nanoparticle, nanofluid, different types of modelings are there. For density, specific heat, thermal expansion, electrical conductivity, dynamic viscosity, all these things are there accordingly. So density, how to consider density? Either you can consider density directly, or with respect to concentration also you can consider. So if you write the density with respect to directly, the rho NF equal to rho S pi plus rho F 1 minus pi. If with respect to concentration you are writing, then second expression. This is the expression. Rho means density, C means concentration for that one. Then thermal expansion coefficient. Thermal coefficient may be obtained from the model 9. This model is there actually. Then we can consider thermal expansion coefficient this way. Then electrical conductivity. So automatically when particles are diffused to base fluid, definitely there should be electrical conductivity, and due to Maxwell, he has obtained the electrical conductivity. There are different types of modelings are there. Generally Maxwell electrical conductivity phenomena or the formula we use in nanofluid modeling, and this is your electrical conductivity for that one. Then dynamic viscosity. Here also different types of expressions are there. As you know that there is not a particular or specific model. Different authors they take it in a different way. So the dynamic viscosity also given by this one, this expression. Then thermal conductivity, which is why for which actually we are dealing with the nanofluids. So thermal conductivity we can define as rate at which heat is transferred by conduction. There is a unit cross-section area. Through a unit cross-section area, heat is transferred. Then temperature gradient automatically exists, which is the perpendicular to the area. And this is the expression K equal to Q cross A delta T. K is your thermal conductivity, Q is the amount of heat transfer, we can say like this. Then, what are the mathematical models for nanofluid flow and heat transfer? So there are two types of mathematical models. One is single phase model, one is two phase model. So, single phase model means what? When particles are diffused, nanoparticles are diffused into nanofluid, because due to the small, very, very small size of particles, they are totally mixed up with the fluid. So, a mixture model we are considering, not individual. But two-phase model means what? It says that if we diffuse the particles into fluid, then for particle, one section of formula will be there. For fluid, another section formula will be there. These two things are there. That is two-phase model. So in single-phase model, there are 3 or 4 equations. Two-phase model, there are six equations. Three for your particles, nanoparticles, three for your base fluid. Two-phase models. Then single-phase model. Although the suspension of nanofluid is inherently a two-phase fluid, but it can be considered as a homogeneous liquid, just now I told you, if some proper assumptions are made. And in single phase models, the governing equations are solved only for an effective liquid phase. So we are not considering separately particle phase. Directly for liquid phase, directly we are considering because particles are very small and they are diffused and they are mixed up with the fluid. They move in unison with the fluid. Then your homogeneous
Hello, sir. Sir, your voice is not clear, sir. Am I audible, sir? Hello, Mishra, sir. Network problem. I think network problem, sir, from your side, sir.
Is it okay now? Is it okay?
Yes, sir.
Okay, okay. Thank you. Sorry for the interruption. Is the screen visible? Is it visible?
Yes, sir. Yes, sir.
Okay, fine. So we are discussing there are different types of models. One is single phase model, one is two phase model. Single phase model means the particles and fluid. There is no slip velocity, but in two phase model there is a slip velocity. So two things are there actually. Then single phase model, these are the assumptions, homogeneous model. The slip between the base fluid and nanoparticles negligible. The size of solid nanoparticles are ultra fine and dispersed uniformly throughout the base fluid. Solid and fluid phases are in hydrodynamic and thermal equilibrium. So that one. So based on that, this is the model of single phase model actually. Yarmar 14, they considered this single phase model based on its only nanofluids. Based on the thermal properties of nanofluids. Nanoparticles have no role to play here. So if we refine this one, the single phase model, then we are getting thermal dispersion model. Then what is the governing equation of thermal dispersion model? With a slight difference, we can obtain the last equation as the thermal dispersion model. This is the equation for that one. Then the next one comes, very, very important significant your model. Many people or many investigators, they have did it for single phase model, but Bongrino decided, and this now latest model is your Bongrino's single phase model. So here what he considered here, earlier the results what are developed by or analyzed by other investigators, Bongrino's model gives the better and refined result as compared to other thermal management systems results for that one, thermal conductivity results. So what he did actually, he took 7 slip mechanisms. One is inertia, second one is Brown diffusion, third one thermophoresis, then diffusophoresis, Magnus effect, fluid drainage, and gravity. All these things they considered. Out of 7 slip mechanisms, he could conclude that, he could reveal that 2 slip mechanisms are very, very important, which enhances the thermal conductivity of nanofluids. One is Brownian diffusion, second one is thermophoresis. Others have less effect, but only thing is Brownian diffusion and thermophoresis. These two are having the high impact for the enhancement of thermal conductivity of nanofluids. He has considered. And according to him, you see, earlier what was happening? You see, there are only 3 equations: continuity equation, momentum equation, energy equation. And due to this, he has considered 4 equations. Okay, continuity equation, equation of motion for nanoparticles, momentum equation, also nanoparticle energy equation. And main point is, earlier continuity equation was there, momentum equation was there, energy equation was there. But this continuity equation for nanoparticles, it was not there for previous investigators. Due to this thermophoresis and Brown diffusion, he introduced this the 4th equation. So all the single phase models except Bongrino, they were having only 3 equations, but Bongrino's single phase model is having 4 equations. And this result and this model gives somewhat better and much better results as compared to other models actually. Then next one is with what we have done. This is our, and this is my team, me and my scholars and my guide, we invested this one. There's a modified Bongrino's model pertaining to nanoparticle concentration. He has considered volume fraction. You see, phi is there. Phi is the volume fraction we can consider. But here we consider C in nanoparticle concentration. And we considered here a new one is with respect to concentration if you take, we are getting better results. So first one here considered Bonus model pertaining to nanoparticle volume fraction, and what we did modified Bonus model pertaining to nanoparticle concentration. So there is a little bit change with the equation of your contributing equation of nanoparticles. This you are getting. Then these are the limitations of single phase model for that one. Then what is two phase model? Two phase I told you already. The string velocity, automatically particle phase and fluid phase. Two different phases you have to consider. Not same thing. So in this case, what happened? There is a Euler-Lagrangian case, Euler models. Two things are there. So Euler-Lagrangian model is also called discrete phase model for that one. Then limitations of Euler-Lagrangian model, it requires high memory and computation time. Then mathematical model of your Eulerian-Lagrangian model. So this is the Euler-Lagrangian two-phase model. We can say like this. This is the model. Then Euler model. So these models categorized in three ways. One is volume of fluid. Second one is mixture model. One is only Euler model. And as you compare these three, mixture model is more popular as compared to other two models. So this is your volume of fluid model. This is the equation for volume of fluid model. It is written in tensor form. Then mixture model. This is the volume equations of mixture model. We can say like this. This is written in the tensor form only. Then Euler model. This is the tensor form of Euler's model for that. This is the model for that one. Then, now what is our invention? Our invention is four coupled governing equations of nanofluid and heat transfer with the electrification of nanoparticles. So our invention is this one. Not our research is on this one. Now we cannot say invention, our research. Our review and research is on this one. So we modified the single phase Bonus model because this is more suitable for the enhancement of thermal conductor nanofluids. So that's why. What is electrification of nanoparticles for that one? Because when particles are diffused, till date, no one has done this one. We have a patent and many publications are also there for that one. When particles are diffused to fluid, Brownian diffusion occurs, thermophoretic occurs actually. And due to Brownian diffusion, if we move one step ahead, what happens? Due to Brownian diffusion, they collide with each other, collide with the boundary of the channel and also fluid particles, because of which the particles are automatically charged owing to the adsorption of ions. So they are automatically charged. So that equation, that part, till date, nobody has pointed out. So first time, we introduced this one and we modified the equation of Bongrino. And see, Bongrino equation was left hand side, right side, two equations are there. And ours is the third one. This is the term what we have introduced because of nanoparticle electrification. Similar for Navier-Stokes equation also, see, this is the last one. This is our term. Similar energy equation also, look at the last term. So, up to this one, it was the Bongrino. We did it for the concentration and we enhanced the model using the nanoparticle concentration and nanoparticle electrification also. And we saw that our model gives the much better result and heat transfer is enhanced as compared to other models. And this is the patent, we did it based on this one. Okay. Then you see there's a comparison with some results. Earlier, this I told you, Das theory model was there, homogeneous model. See, three equations are there. Using this model, minus theta dash is heat transfer enhancement. How much heat is transferred? So see, it is 0.27375. Using this model, heat transfer, theta dash is heat transfer. Heat is transferred this amount. Next, another is Neil-Kuzma model. So Neil-Kuzma model, homogeneous model, if we use this model, different models, then our heat transfer is this much, 0.57134. Enolan-Bechuk model. This is another model for homogeneity. Using this one, it is somewhat better, 5727204. It is the heat transfer enhancement. But if you say Bogner's model, non-homogeneous equilibrium model, Bogner's model, original, its heat transfer effect is 0.59379. But if you go for the present model, what our model, you see heat transfer is 0.80461. Slowly, as compared to other models, you see heat transfer, our result is much more better than other results. That means this is we claim now. That's why we obtain this patent actually. Okay, so we claim that our model is somewhat better than as compared to other models. For that, there are different CFD techniques. How to solve CFD techniques, computational fluid dynamics techniques, to solve the nanofluid flow equations. That means we are getting these equations. How to solve these equations? So there are different methods are there. Macroscale based technique, mesoscale based technique, microscale based technique. Three are there. Macroscale and based techniques are finite difference method, finite volume method, finite element method, control volume finite element method, boundary element method, spectral method, messless method. These are the methods. Mesoscale and base techniques. These are what? These techniques to simulate systems at a scale in between molecular scale and macroscopic scale. And there are two types of macroscale techniques. One is lattice-Boltzmann method, one is dissipative particle dynamics method. Then third one is the microscale based technique, molecular dynamic simulation method. So in this case, the molecules and atoms are regarded as the fluid particles, whose dynamics and interactions are. And finally, this is the conclusion. The two-phase approach gives results that are generally closer to explained data. And in geometrically simple problems such as natural convection cavities, instead of employing a single-phase homogeneous approach, the heat transfer rate can be estimated easily just by using accurate models for the nanofluid thermophysical properties. Review of literature suggests that two-phase mixture model is the easiest approach to apply among two-phase models. And in a single-phase approach, using novel models for thermophysical properties instead of classical models can reduce errors in prediction of heat and mass transfer flow characteristics. And the finite volume method is the mostly used numerical approach for simulation of mass. This is the excellent method, finite volume method. So this is the bibliography. So thank you all.
Thank you, sir, for your session on nanotechnology and fluid dynamics. We are very thankful to you for joining this session in our international conference in advancement in science and technology. Thank you. Now we have with us Professor Dr. Sambit Prasanjit Naik sir with us. We have second session of Sambit sir. So on behalf of our Phaltan Education Society's College of Engineering Phaltan, I welcome Sambit sir for this international conference. And Sambit sir completed his PhD in Engineering Geosciences from IIT Kanpur, and currently he is working as a research professor in Active Fault and Earthquake Hazard Vegetation Research Institute, Pukyong National University, Busan, South Korea. So before wasting much more time, I request Sambit sir to start his session. Please, sir. You are not audible, sir. Voice is not getting clear. No, sir. Not yet, sir. Please unmute yourself, sir. I think you are not unmuted your mic. Please unmute your mic. Yeah.
Yeah. Good morning, everyone.
Good morning, sir.
Actually, thank you for giving me opportunity to present, like, so some of the work. Although my work doesn't fit to the theme of the conference, but I think for building a advanced India, so we should have a seismic safe society. And we should have properly understand the seismic hazard, and then we can implement these techniques the result to have seismic safe urban designing, and then in that way we can contribute to the advanced society. So as we know, we have 1 minute. So is it visible my screen?
Yes, sir. Screen is visible.
So as we know, we have around 10 to 12% of total natural hazard is earthquake, and then it's more devastating than other natural hazards, because we cannot exactly predict the timing of the hazard. So for that, we have to understand the past, we have to learn from the past hazard. So how we can learn from the past? We have to detail map, mapping the earthquake hazard, the damage, or the to the built environment or to the natural environment, and then we can keep record on that of that, and then we can use that for the hazard modeling. So due to as we can see, you can see these are the two pictures are from the recent 2023 Turkey earthquake. So you can see all the buildings completely collapsed, or some of the buildings still standing after the earthquake, but it is not going to be habitable. So in that way we have to map detail the damage to the built environment, to assign the to give to understand the effect of the earthquake. And then we have to map the when we have a big earthquake, so it causes the surface rupture. That means it cracks the ground. So we have to detail map those kind of features, so that we can use that for the how the intense was that earthquake. So for that we can use different techniques, traditional and advanced techniques. So I will show some of the this slide is when we have a big earthquake, big earthquake. So the intensity, the damage is around close to that epicenter. It's more. Then gradually, when it goes far, so the intensity goes will be lesser. So in that way, we have to map. So when there is a earthquake, so we can see the surface rupture, and then liquefaction, and then landslide, and then tsunami. So it can cause lot of damage to the building, or road, or any kind of utility, even nuclear power plants, something like that way. So why we the mapping of these effects is important, because we can assign the seismic intensity for each of the locations. So in that way we can keep we can maps, prepare some map using GIS techniques, and then we can keep as a record, online or offline form. So we can use that for future future seismic hazard assessment, or future building design, or nuclear power plant design, or any kind of lifeline structures. So for that we can use although we can go to field and then map those
Sir.
individual.
Hello. We are still on the first slide, sir. Screens are not moving.
Okay, right. Sorry, because I thought it is, but in my in screen it is showing I am the exact the slide which I am presenting. I don't know. Let me like stop sharing and then start again. Is it okay now? You can see different slide. Hello.
Yes, sir.
Now you can see.
Now it is visible.
So like we can use high-end technology like LiDAR and then UAV for detailed mapping after the earthquakes. So then like that will, these techniques will give you like lot of data in rapid way, like because it's during when you have big earthquakes, so it is difficult to go on site from each site to map the damage or map the effect like surface rupture, liquefaction, all those features. So we can use this kind of like remote sensing techniques to map in a faster way, so that we can understand the how damaging this earthquake, so we can share the data with the agency those who are dealing with the hazard response survey or like relief survey, like that way, so they can reach in proper particular that location, and then that will facilitate your hazard response survey. So like I will not go in detail with what is LiDAR or something because LiDAR, like as we know, it use the laser pulse from a flight, and then it detect like the surface or the tree or the surface. But I will tell like when we have a like normal satellite image that include the tree or like all the effects. But in LiDAR, we can remove that tree. That is the like a tree or any obstacle. So that is the like advantages of LiDAR, having LiDAR data. So we can exactly get the precise ground from the ground data. So that is, in that way we can, suppose there is a rupture, so like surface rupture, so we can measure exactly how the ground has shifted, or how the ground is going up or going down in that so in that way we can exactly assess the exact dimension of that particular location, and then we can give some intensity. So I'll show you some case study after this. So second is insert data. So we can see like how from the like when there is earthquake, so we can get the pre-earthquake or post-earthquake data. So we can do the image correlation using any remote sensing software. Like specifically, I use Snap tool, which is a free software. So and then you can like detail map, like in this image you can see this this line is the surface rupture caused by the 2023 Turkey earthquake. So then we can know this is the most, like since this is the surface rupture area, so this will be probably the highest affected area. And this is another, like they have two earthquakes, so two earthquake cause surface rupture. So these kind of techniques like help us to fast tracking the damage. So then we can go to the field, and then from this, and then we can exactly pinpoint some point to go the field survey. So then we can go and measure the field. So how we can cross check these techniques, because when we go field, we can measure that amount of like displacement or amount of damage, and then we can validate with the remote sensing data. So these are like proven like high-end technology to map the hazard or the effect of the earthquakes. So another is we have UAV. So after the earthquake, so we can like fly the UAV and then get the exact scenario data, and then we can use that one in the we can pre-process or pre-process in some software, and then we can use that one in the remote sensing software to exactly map the damage. So secondly, third is we have also very high end nowadays satellite data. So this image is showing the building damage from the different from the satellite data during the Turkey earthquake. So you can see when we have the pre and post earthquake satellite image, so we can process and then we can prepare the proxy map to know the building, because when in the pre image it shows the height of the building, and then so after the post image, suppose the building collapse, so we can make this kind of typical heat map when we generate in NDVI or something like that way. So then we can also map landslide, or we can track the landslide even. So this is one landslide which was initiated before the earthquake, and then during the earthquake it got activated and it make a huge landslide. So in that way we can so from the satellite image, if we can calculate the area and volume of the landslide, because it's very difficult to reach that point. So in that way, remote sensing technology help us to know the exact volume of the volume or area of the landslide. So if we know the volume or area of the landslide, so we can estimate the seismic intensity. So I'll show you. So from the building actually, so when we have, how we can estimate the seismic intensity when we have suppose different building damage criteria they adopt. In India we use MSK intensity scale, but internationally they use modified Mercalli intensity scale. So from the different grade of building damage, so we can give the intensity. But and then similarly there is another intensity scale. It is environmental seismic intensity scale, which doesn't include the buildings actually, because buildings, when we include the buildings, sometimes when we have very developed country, the buildings are earthquake resistant, but that doesn't mean that the similar earthquake if occur in a developed country or poor country, so it will not create damage or something like that. So that's why, so we it's better to use both, integrate both the intensity scale. So how we can do, I'll show you the in the next couple of slides. So these are advanced techniques which I am using for the seismic intensity estimation. So I'll show you one case study from Indonesia. So in 2018 there was a big earthquake, 7.2 magnitude earthquake occurred in in Palu, Indonesia. So which caused before that we can I will give you brief brief understanding about the Indonesia. Indonesia is situated in ring of fire, so it is more prone to earthquakes. So these are tectonic boundaries, and then the red lines you can see. I don't know how much you are familiar with the fault or something like that way. So these red lines are the fault lines caused by the plate movements. So the earthquake occur around here, the epicenter, it is 7.5 magnitude earthquake. So since it was a big earthquake, so it caused surface rupture. So it was the second damaging earthquake in Indonesia after the 2004 Indian Ocean tsunami. So you can see the how the damaging, the buildings are completely collapsed. There is no it became pieces. So it caused 4,000 people died, and then around 5 lakh 37,000 people were displaced from their house. So it caused around 70,000 houses damaged. So that's why we need to understand the earthquake hazard in in a proper way. Although in India recently we don't have big earthquake, but in the past, in 1950, 1934, we have big earthquakes, are more than 8 magnitude earthquakes. So that if this kind of earthquake occur in that time, there is no development, no like concrete buildings or no like big road or rail network. So now if that kind of situation will occur, so it is going to be more damaging or more devastating. So this area, this area shows like these area are affected by tsunami, this red line. So I like in what I did like I map all the effects like from the remote sensing and then from the field. So you can see like the coconut tree here. So it like it was in one line before, but it is displaced because the fault line passed through here, and then you can see the road also displaced. So this is the location of the fault, and then you have landslide, and then you have like ground cracks, and then this is tsunami. So there was a very big bridge here connecting between two parts of the city, but the bridge completely collapsed because of the effect of the landslide, and then you can see tsunami that the like masjid is completely crossed. And then so I classify the different effects of the earthquake. So ground cracks, liquefaction, surface rupture. So and then so the surface rupture was 37% of total damage. So like how I use the INSA data. So and then you can see the surface rupture, this displacement, this line is clearly the fault passing through the city. And then so from I process the image correlation technique. I use image correlation techniques, and then so from the pre and post INSA data, so I map you can see the fault line here. So exactly what so after that I can take some points I took to the QGIS or ArcGIS software. So you can select each point at a regular interval, so you can get the displacement due to the earthquake. So you can see it is the fault, the earthquake caused around 7-meter offset of the on the ground. So that offset caused a lot of building damage. So how I validated this one? So we took UAV image. So you can see the this line. So where the rice palms are past the fence of the rice palm of the boundary of the rice palm is displaced around exactly 7-meter. So somewhere at some point I exactly don't remember. So in that way, so I trace all the location and give latitude, longitude, and then create a database. And then also tsunami. So you can see these points are tsunami inunded, the house damaged by the tsunami because the seawater entered to the inward land, landward. So then you can see the effect, how the effect of tsunami was there. This masjid was on land, now it is in the sea. So this tree was also it's cherry blossom tree. So it was on land, but now it is inside the sea. The ground subsidence and then occur during the earthquake. So this shows the tsunami water enter to the someone's house, and then it was left a mark. So I also create the database from the field and then from the remote sensing data. So this is another interesting phenomenon was observed during this one. So, am I audible now?
Yes, sir. You are audible.
So yeah, so you can see because these are coastal areas, so it is very difficult to in detail mapping because the land already disappeared. So I use pre and post satellite images. So you can see different volume of the land already submerged in the sea. So and then so when we go field and then we collect some data from some of the locations, and then but we can estimate the land after the earthquake due to the tsunami or the coastal landslide after the earthquake. So we can use that volume for the seismic intensity. So similarly, like I calculate the volume from the remote sensing techniques. So similarly, like landslide, because some landslide along the road, so we can easily trace, but interior like hilly area, so it's very difficult to map by the field. So in that way, we can use remote sensing techniques to map exactly each and every landslide, and then we can estimate the area and volume. So this is the landslide distribution map. You can see how much area it is covered. Like it's around more than 3,000, 4,000 square kilometer area. So it is very difficult to cover immediately after the earthquake, or even after years of the earthquake, we cannot cover this area. So in that way, remote sensing techniques can help us to map more accurate way. So we can, and then we can validate some of the location in the field if possible. So in that way, we can know that our whatever data I am collecting is correct. So in that way, I trace around 8,000 landslides from the from the field, sentinel data, and satellite images. So and then I calculate all the volume of all the 8,000 landslides from the area, and then we can use that one for the landslides. So there are liquefaction. You can see this is pre and post land satellite images. The pre, there was completely village or city in that area, but after the liquefaction, this whole area is washed away. So there are several big such liquefaction related landslides. So from so it is very difficult to map each and every liquefaction points. But so from the satellite image, we can see this image shows the pre-satellite image and then post. So you can see some patches of water on the ground, or sand came from the deep, and then so I trace all the liquefaction feature, and then so we can tentatively measure the area or radius of the landslide, these sand boils. So then we can use that for the seismic intensity. So then similarly ground cracks, so we measure and then collect that way. So then I'll briefly introduce the seismic intensity. As I told, we have the modified Mercalli intensity, which is worldwide use, but in India we use modified MSK intensity scale. So there are it's generally 12 grade intensity scale, but it have different criteria how we can assign the intensity. But when the earthquake is big or more completely damaging, so we cannot distinguish the grade between 10 to 12. But when we have a record of the surface rupture, ground cracks or slope movement, landslide or something like that way, so we can go beyond, we can cover that gap between the seismic intensity 10 or to 12 when we have. This one is completely based on the damage on the built environment, human related, house, how you failed, how you move, that way. But these are all on the ground evidence. So in that way, I prefer to use this environmental seismic intensity scale to damage this assess the seismic intensity. So each of the ground effects has different criteria how we can assign the intensity. So in that way, so so total I use around 7,400 more data sets to assess the seismic intensity for this Palu earthquake. So the earthquake caused around 170 kilometers surface rupture. So I give there is some formula. So use the surface rupture length to so the seismic intensity is 10 or 11, that way. So then for each location which I mapped from the field or from the remote sensing, so we give the intensity, and then we can compare with the instrumental intensity modified Mercalli intensity scale. So you can see the difference. So this is in like intensity, or USGS give the when there is earthquake. So USGS generally, United States Geological Survey, gives some intensity because they have some seismic stations. So they give the high maximum intensity around like 7 or 8. But when I map the ground effects like surface rupture, liquefaction, ground that way, so the intensity is 11. So in that way, then I prepare this map in in the GIS platform, and then I can provide this map to USGS, or the suppose in India we have when the Ministry of Earth Science, the seismology division. So I can suppose there is a big earthquake in India, so I can map this kind of things using remote sensing techniques, and I can share them, so they can club off both like their data and then our data, and then they can make some intensity map, which is more crucial for the seismic hazard assessment. So so basically, so this kind of study is crucial for damaging earthquakes. Like we can implement for this kind of study for the historical earthquakes. Like so, I did for like if you remember in 2001, there was a Bhuj earthquake. So and then before that, in that area, in 1890, there was another big earthquake, a Lavand earthquake. So that earthquake caused the how say the disappearance of the Harappan civilization. So I use this kind of techniques for those two earthquake, and then that study is already published, and then in that way. So the we have like this is the most cost more effective seismic hazard assessment for future, and then if when we have this kind of map, so we know this, like suppose I am going to build a nuclear power plant, or like heavy power station, electric power station, or dam. So I know like this I like when this kind of map is publicly available, so we can say like they can see that this area is having going to have like seismic intensity 10 or 11. So they can design like they have to like suppose they are planning to design the building, so they can allow the civil engineers or the like engineering guys. So like this my study area is going to have higher intensity, so they can design the structure in that way. So they can consider maybe this site is going to have liquefaction, so they build the foundation in at a deeper depth, so they can prevent liquefaction like that way. So these kind of things we can use for the earthquake early warning systems, or the we can use for the implementation of like seismic design building codes. So this is discussion and conclusion. Like the recent advanced space technology helps in diverse ways for a better seismic hazard assessment. So it enhances the data quality and quantity, and then time of the data collection. So by the first data collection process, we can analyze the data and then plan in the disaster mitigation and restoration in a fast track basis. So this is my end of my talk. Thank you. So if you have any questions.
Thank you so much, sir, for your session. If anybody is having question, they can ask.
I don't know the audience, like mostly civil engineering.
The audience are not having any questions, sir. So we can end with this session. And thank you so much, sir, for your session. Okay. Thank you, sir.
Thank you.